Well, as we just mentioned, PIM is responsible for getting us through layer 3 devices and getting a packet from when it first arrives on one of these routers via the source all the way through the network, properly replicated, by the way, as it goes. So one packet here, splitting into 2 packets here, and then getting it to the destination routers, which will deliver it onto the network where the receivers are. Now, we call it protocol independent multicast for a reason. Protocol independence means that we do not care what the underlying unicast routing protocol is. So this is a very big part of the multicast architecture, is we ended up as an industry building this, we call it PIM, such that we can use EIGRP, we could use OSPF, we could use RIP if we really wanted to, we could use BGP, and we could use static routes. It doesn't care. What it really cares about is that we have layer 3 convergence. We need to make sure that we can access all of the subnets in the network and that it is stable. We don't want routes flapping around because that will cause disruption to our multicast environment. Now, PIM actually behaves a little bit like an IGP. And the reason for that, this IGP behavior, and when I say IGP, I'm talking about these routing protocols, EIGRP, OSPF, and whatnot, but it's going to form neighbor relationships, and it's going to do so via, well, multicast, which might seem a little chicken and egg from the perspective that I need PIM to use multicast, and yet here I am using multicast to form PIM relationships. But this is local multicast. So these are specifically going out and just trying to get out to the other routers on a layer 2 segment without bothering all the other hosts. It's why we use multicast between EIGRP and OSPF neighbors, for example. So we're doing the same concept here, but we are just forming relationships up here on the network between our layer 3 devices. So we're going to exchange messages. We could do a show IP PIM neighbor, for example. And that's going to show that we've got neighbors on the other side of whatever connection we have. Now, these multicast addresses we should be a little familiar with. It's going to be using 224.0.0.13 for PIM in the IPv4 space. And once again, we're going to find that the IPv6 multicast address is very similar. Just keep in mind that IPv6 uses hexadecimal. We might expect it to end in 13, and it does end in 13, except 13 looks like a capital D, because that would be 13 in hexadecimal. So we're exchanging these multicast messages, we're forming PIM neighbors, and ideally, at the end of just setting up PIM, we've got all of our routers communicating with one another in this space. Now, the goal of PIM is, well, there's actually a lot of goals, but we are going to start to install multicast routes, which starts to feel a little bit more like that routing protocol behavior again, except multicast routes, they have some similarities to unicast routes, but they're also extremely different. Okay, these multicast routes are not, well, here, I'll say it like this. They are not exchanged. When we talk about EIGRP and OSPF, we talk about exchanging routes, making sure that we tell each other about the routes that are attached and all of these things. And that's not exactly what's happening with multicast routes. Instead, what we're doing is we are forming trees. The goal of PIM is to form these multicast trees. And just like if we think about the word tree, we also see that in the word spanning tree, for example. Just like with spanning tree, the goal of a tree ultimately is to create a loop-free topology for traffic to flow down. So I can allow traffic to flow, say traffic flows here, which means that regardless of where the multicast source is, regardless of where the receivers are, we can expect that our multicast traffic is going to get from end to end. Now in our topology in the top left, we didn't make a looped environment, but let's say that we have a connection here between these two routers on the right. We form a PIM adjacency there, so now we've got all of these different PIM relationships. Well, a tree, a multicast tree, might look something like this. We've got the source, we've got the receivers, but the last thing we would want, for example, is to have multicast looking like this. Because now I send a packet, it gets sent down like this, they get sent back and forth, and now all of a sudden we've got a routing loop. So instead, PIM wants to form a loop-free topology, and so it might look like this, it might look like this, but either way, this concept should feel very similar to spanning tree in that we're trying to create that loop-free topology that simply allows traffic to flow from one end of the network to the other, such that, again, our source can transmit the multicast traffic to the receivers. Now, multicast routes come in two different forms. Let me change colors here. So we have what we call the star, G multicast entry, and then we also have the S, G multicast entry. So let's talk about both of these. So a star, G, I equate this to sort of a template. It's showing us what we want to do when multicast traffic arrives, but importantly, no multicast source has been discovered. So we have no source yet at this point, but we do have receivers. Keep in mind in all of this that a source might be the first one to show up, or receivers might be the first one to show up. We might have receivers that are waiting for multicast traffic to show up, or we might have a source that's trying to send multicast traffic onto the network and there's no one there to receive it yet. And so we've got to be thinking from an architecture perspective that any of these things can happen, right? We could have the receivers there with no source, we could have the source there with no receivers, or we could have ultimately sources and receivers at the same time. And so we have to think about things from that perspective. So what happens, again, if I have receivers on the network, but I don't yet have a source? Well, we'd install the star, G route. And what the star, G route gives us is it gives us a list of outgoing interfaces. Now we have a fancy acronym for this. We call it the outgoing interface list, or the OIL, or we could call it the OIL, I suppose. Usually the OIL is what we refer to it as. Sounds a little weird to talk about oil on our routers, but I guess maybe some of them could use a tune-up at this point. Let's be real. But either way, we'll just call that the OIL. And it tells a router where to direct the multicast traffic. So if I've got a router like this, and I've got 4 different interfaces, the question is, where are their receivers as far as PIM is concerned? So if there are receivers out this interface and this interface, well, I'm going to have those in the list. So let's say this is gig 00 and this is gig 01, and then we'll just say gig 02 and gig 03 are up here. Well, the OIL in this case will have gig 00 and gig 01 listed. And so the reason why I call it a template, and I'm just going to put quotes in there because that's more of a Jeff Kish thing than anything you'll necessarily read. But the reason we call it a template, or I call it a template, is because when multicast traffic inevitably arrives, so now all of a sudden we have real traffic show up, we need to know what to do with this traffic. And the OIL tells us exactly what to do with it. Send it out gig 00 and send it out gig 01. So now we need to talk about this S, G group, or S, G route entry, which I ran out of space there, so I'm erasing it so we can talk about it down here. So now we have the S, G. The S, G says that we now have a source. That's what the S stands for. The source is a specific source. This is an IP address. It might be something like 10.1.1.1. If our source, let's say up here in the diagram, is 10.1.1.1, like that. Well, now we've got this entry, and you'll notice that when we said star up here, now we kind of know what the star meant. Star or asterisk is very commonly used as a wildcard, and so we're truly saying any source. It doesn't matter what source comes in, or what source generates this traffic. I have a group address like 239.1.1.1, and I have receivers that want this group address. And so I don't care which source generates it. All I know is when traffic is received, I'm going to send it out these specific interfaces. Well, now that I have a source, I can build an actual S comma G entry that is based on this template. And so I can say that my S comma G, so 10.1.1.1, comma 239.1.1.1, this entry, again, S for the source, G for the group, has an incoming interface. Let's say it comes in here this time. So incoming interface is gig 02, and the outgoing interface list I simply pull down from the template. So gig 00 and gig 01. The template rather tells me that OIL, it populates it for me because I know that there are receivers out those interfaces. Now, multicast, very importantly, will never bring traffic in on one interface and send it out the same interface. That could create loops. So let's say that we actually got this in on gig 01. Were there receivers downstream there? Yeah, but we have to assume that they have already gotten the stream or that they're going to get the stream another way. So in that case, if we said that the incoming interface is gig 01, I would still use this as a template, but I wouldn't include gig 01 in the outgoing interface list. So that's again where the template concept comes from, where it says, okay, we know all the interfaces that we want to send this multicast stream out, but we can't send it out the interface that we received it on. And so it's very important that we identify what that incoming interface is. Now, one of the reasons why it's so important that we recognize that has to do with the fact that, again, we are trying to generate loop-free trees or loop-free topologies. Now, the way that PIM performs this loop-free concept is it relies on the fact that a unicast environment is loop-free. This is part of the protocol-independent multicast. We are relying on this point here that we have layer 3 convergence. So if the unicast environment is loop-free, we can base our multicast environment on the unicast environment. And so we're going to use a check that is pretty popular in the networking world. We call it the reverse forwarding or reverse path RPF check, a reverse path forwarding check. And I'll just put that in here, RPF check. The RPF check is going to take a look at that incoming interface. So right here, we said that we have an incoming interface for this S comma G entry of gig 01. And so, and specifically, by the way, we said that we're using this IP address of 10.1.1.1. So we are going to perform this check. How do we perform this check? Well, we are going to check the unicast routing table to find out what the outgoing interface would be. Basically, if I were to want to send a packet to 10.1.1.1, where would I send the packet? So I'm going to check that and find out, okay, would I send it to gig 0 or send it out gig 01? If I got a packet in to the router destined for 10.1.1.1, would I then send it out gig 01? That's the reverse path forwarding check. I received multicast from this source address on this interface. I want to make sure that if I were to send traffic back to that source, that it would go out that interface. And if so, then that is good. But there will be times where we say, no, actually, I would have sent that packet out gig 03. And so if this isn't the case, then we will reject this multicast traffic. We will drop it. We will not install the S comma G route because ultimately that means that we have a loop in the network. If we look at the top left, essentially what that's saying is, let's say that our traffic is actually coming down. I'm trying to find a color that will work here. There we go. So we send multicast traffic out. It goes to these two different routers. And then this router on top wants to send it down to this other router. Well, we know that that would create a loop. And so ideally what's happening here is I get it from 10. So the source is 10.1.1.1. But this router knows that the routing table says to send it this way. And so at that point, I have two different options to choose from. I have these two different packets showing up. I can't accept both of them. I only need one. So I'm going to check that routing table. Since the routing table says that this is the path towards 10.1.1.1, I'm going to reject the packet that's getting sent down from the other router, and that again creates that loop-free topology. So the RPF check is a big part of our multicast world. We need to understand that that is going to cause us to drop packets, and if there's ever a problem with RPF checks dropping our packets, then there might be a problem with our unicast topology, because again, we are making some assumptions, especially around having a converged and stable layer 3 environment.
Thanks for watching. Be sure to click here to subscribe to CBT Nuggets and click the notification bell to make sure that you're aware of every time we post new content. If you're interested in a career in IT or you want to brush up on your IT skills, then swing over to our website, and while you're there, be sure to sign up for a free trial.